Hello and welcome to episode 10 of Data Every Day. Today we'll be looking at some unlabeled data about mall customers and using k-means clustering algorithm to perform market segmentation. So let's take a look at the data, and we can see it's a very simple data set of only 200 examples and 4 different columns: gender, age, annual income, and spending score. A score assigned by the mall based on customer behavior and spending nature. Alright, so let's get into it. Hold on, let me just bring this down. Okay. Now I'll just do this. So we'll start by importing our normal libraries, NumPy and Pandas, and our matplotlib, which will play an important role in today's video. So by the end of today, we will be able to cluster the market data into various segments and be able to visualize it using principal component analysis. Alright, so we're going to need a label encoder to convert the gender data into numerical values. And let's see, what we're going to need a standard scaler to make the both the k-means clustering and the principal component analysis run smoother. Okay, so we're going to need our k-means. Oh, wow. And we're going to need decomposition, our principal component analysis. Alright, and we can just run that, and I'll make a markdown here. Getting started. Alright, so we'll load up our data. Read CSV again, as usual, right here. And let's take a look at it. Alright, so it's only 200 rows. So, with k-means clustering, this won't be a problem. If we were trying to learn if we were trying to predict based on a classification, or if the data was labeled and we were trying to perform supervised learning on it, this would be a very small number of examples to use for such a task, unless there's a very clear relationship between the data and the labels. But since we're only doing unsupervised learning, and we don't care about classifying the examples, this is fine. It doesn't really matter how much data we have. We're just trying to find segments within the data that have some sort of underlying pattern. Alright, so we're going to start by pre-processing our data. So pre-processing. And we will start by dropping this customer ID column, because we don't need it. Customer ID on the first axis and in place. Well, really it's the second axis. It's the column axis. Okay, so we take another look at it. This guy's gone. Now we just have 4 features, and we want to convert these male and female values into zeros and ones. Male will be 1, female will be 0, as per the standard convention. Alright, so we'll use the label encoder for that. And we will say data, the gender column will be equal to our encoder dot fit transform the gender column. So we're fitting the encoder to our gender column. So it's going to find all the unique values in the gender column, and it's going to assign each value to a numerical label. And we're going to have to, oh no, we don't have to write anything here. Okay. And after it does that, we're just going to make a variable called gender mappings, which will give us the index and label as a dictionary for each mapping that it performs. And the encoder has a attribute called classes, which we will use to see this. All right, and let's just take a look at that. And you can see female has been mapped to 0, male has been mapped to 1. Perfect. Okay, so now we're going to scale our data. So we'll use the standard scaler that we imported, and we'll call it scaled data. And we're going to, here, we'll do it this way. Scalar dot fit transform data. And we're going to turn this, because this will return a NumPy array, we're going to turn it back into a data frame so that we can do further processing on it. So data frame, and we're going to specify that the new columns should be called what we had as the old columns. Alright, so if we run that, and then we'll take a look at what it looks like. Same as before, except all the values have been scaled to have unit variance. So this will make it a lot easier to cluster the data. Every feature is on the same scale. Alright, so now we're getting into the clustering. We're going to decide, basically, we want to know how many clusters to use. And there's a convenient trick called the elbow method that will allow us to choose the number of clusters. But first we're going to have to set some maximum number of clusters, so we'll call it max clusters, and I think 50 is reasonable. So what we'll do is we'll fit a new k-means clustering algorithm to the data 50 times, each time with a new number of clusters, starting from 1 to 50. So max clusters is 50, and now we'll do that right here. We'll call it k-means tests. So this will be a list of all of our different k-means algorithms, in which each one is using a different number of clusters from 1 to 50. So k-means tests will be full of k-means. Well, let me put it this way. All right, k-means will give us a model to fit that we can use to fit our data to. And we're going to specify the number of clusters in each one. So we're going to have this range from 1 to 50, right? So we're also going to specify, let's call it I, the n in it. So what this is saying is, because of the random initialization of the k-means clustering algorithm, we run it 10 times and then choose the best result of all the 10 so that we don't get bad results. The more times we do this, the more accurate our clustering will be, but the slower and more computationally expensive it will be. Alright, so we'll keep it at 10, which I think is the default value, but it's nice to specify that. Alright, so this is going to be one k-means model, we could say. So we're going to put that right in here, and we're going to have that for every I in the range from 1 to max clusters. See? So it's going to choose a different value of I from 1 to 50. And it's going to make a list of all those different models with different number of clusters for each one. Okay, and then after that's done, we're going to calculate the inertia of each model. So if we just take a look at it, sklearn inertia, k-means. The k-means model object has an attribute called inertia underscore, and it's the sum of squared distances of samples to their closest cluster center. So basically we're going to plot the number of clusters against the inertia for each model with that number of clusters. So we're going to say inertias is going to be the k-means tests, the ith k-means test. So remember, we have 50 of these. So for each one, we're going to fit it to the scaled data, and then we're going to get the inertia for that fitted model. And we're going to do that for every I in the range, the length of k-means tests. So for each one of these, we're going to get the inertia after fitting it to our scaled data. And we're going to store it in this list inertias. Alright, let's run that. And now we're going to plot the inertias as a function of the number of clusters. So let's get our figure size here. We'll make it small, so because this doesn't really have to be big, we'll make it 7 by 5. And we will plot on the x. We'll have a range of the number of clusters, what we used here, a range from 1 to max clusters, and on the y, we're going to have inertias. We'll put some labels here. Our x label will be number of clusters. Whoops. And our y label will be inertia. Okay. And call it choosing number of clusters. Okay, let's show the plot. And here we can see, this is why it's called the elbow method. There's a certain point where it makes a sort of elbow. This, remember, it's a measure. The inertia is a measure of the sum of squared distances from each example to its the cluster centroid that it's assigned to. So you can see, as we have more and more clusters, the sample's distances from those cluster centroids decreases. So at a certain point, you can see it doesn't decrease as much because we just have it's like redundant clusters, too many clusters. It just doesn't make sense. And up here, there's not enough clusters because all the samples are too far apart from the cluster centroids. But there's a nice happy medium here, right around 10 it looks like, in which we have, well, it's called the elbow method because it looks like a little elbow. And that we'll use 10 as our number of clusters for our actual k-means model. So let's go ahead and say k-means. This will be our official model. It's going to be a new one, except here we'll say n clusters is 10. And we'll leave the n in it as 10 as well. Okay, and then we're going to fit it to our scaled data. Okay. So let's note that we can get the assigned clusters by calling the k-means.predict. So this is going to assign a cluster to each one of our training examples. And let's store it in clusters. So you can see each one of our 200 examples now has a cluster assignment. And there's 10 total clusters. So some examples are assigned to 0, some examples are assigned to 1, some to 2, some to 3, and so on, all the way up to 9. And so I think we are ready to try to visualize this in a better fashion. For that, we will use principal component analysis, or PCA. So we'll create a PCA object using sklearn's PCA, and we'll say the number of components, of principal components, is going to be 2. We're using 2 because we want to be able to graph it visually. We're only using PCA to get a better sense of the data. this is our actual result, right? We've clustered every single training example into a certain cluster or a market segment, but this is going to help us understand and see the data in a better fashion. So we will we're going to reduce our data, so we'll call it reduced data. And by reduced, I mean we normally had 4 features, but we can't graph something in 4-dimensional space. So we're going to reduce it down to 2 dimensions. So we'll now have 2 features, and it will be in 2 space, so we can graph it more easily. So we will, okay, here we're going to do pca.fitTransform, our scaled data. So we're going to take our scaled data and we're going to reduce it via the transform function after it's been fit to our PCA object. And so this again will return a NumPy array, but let's turn it back into a pandas data frame so that we can have a nicer view of it. So we'll name the columns here PC1 and PC2, principal component 1 and principal component 2. Alright. So now if we just take a look at what that looks like, we now have the same 200 examples from before, except their feature data has been compressed down into 2 different features, principal component 1 and principal component 2, instead of our original 4 features, gender, age, annual income, and spending score. So with that, we can notice, okay, before we move on, let's notice our original k-means object here has a attribute called cluster centers. So k-means.clusterCenters underscore looks like this. So this is the location in 4 space, 4-dimensional space, of each cluster center. And there's 10 clusters total. So there's 10 different locations of the center for which, by center it's the average, you can imagine a bunch of different points. You can imagine the centroid as the point that is minimizes the distance between all of them and the center. So this is the location of our 4-dimensional cluster centers, but we're going to use PCA, the same model that we've already fit, to transform them down into 2-dimensional cluster centers. So we'll call it reduced centers. Will be pca.transform. Remember, we already fit the PCA model. .transform k-means.cluster-centers. So we're going to take this and transform it down to be only 2 dimensions. And we'll just take a look at that. There it is. So we had this 4-dimensional data, and now we get this 2-dimensional data. And that's very helpful, because now what we can do is we can plot all of our new samples in 2 dimensions, and then show where the centers for each cluster are. So let's go ahead and do that. Alright. So let's call this data visualization. Okay. So we're going to want to plot a scatter plot of all of our examples, and what we're going to do is color each cluster differently so we can tell them apart. So before we start, let's notice we can target only the elements of our dataset with this dataset with a specific cluster. If we say this, okay, let's put it here. We're going to add, here remember our reduced, where is it? Reduced data here, right? Okay, here I'll put here. Our reduced data looks like this. Let's put another column that has all the assigned clusters for each example. So we'll say reduce data, and we'll call the column cluster, is going to be equal to the clusters that we created earlier. So all these are just going to get appended onto the end of the data frame. So we'll run that. And now if we take another look at the reduced data, you see each data sample has a cluster assignment. And so that's now what we can do is plot each one and color it based on its cluster assignment. So let's note that we can target only the examples with a certain cluster by saying this: reduce data cluster equals 0. This will return a list of Boolean values which equal the truth value of this statement. So you can see if we made this 7, the first two should be true because the first two are classified as 7. So this is saying take reduced data, check along the cluster column, and then return a value for each time the cluster column has a value of 7. And then it puts it all in the list. So what we want to do is we want to take this and select all the examples, basically the data frame only containing examples where we have a true value here. So what we'll do is we'll just say reduce data and use that as our indexer. And now you can see, here it is. It's our whole data set, but only containing the values, only containing the examples where we have a cluster of 7. So let's say what we want to do now is we want to take this and we want to plot PC1 against PC2 in a scatter plot. So that, and we're going to color it a certain color because they're all in the same cluster. So what we can do to get only PC1 is use the LOC function for pandas, all rows, and just PC1 as the column. And that will give us only the PC1 column, but for only examples that have cluster 7. Alright, so what we'll do here, and note that we could change this to PC2 to get the PC2 values for cluster 7 assignments. So what we'll do is we'll take that, right, and we will plot, say this, okay, let's first do our figure size. We'll make it bigger this time, 14 by 10. And now we're going to do a scatter plot in which our x value will be what we said before, the PC1 of only clusters of only examples assigned to a certain cluster, and our y value will be the same thing but PC2. So now we're going to change 7 to 0 to mean the first cluster. And now so we're going here. I'll just plot this so we can see what it looks like. So this is all the examples that have been clustered into the 0th cluster. If I change this to 1, this will become all the examples clustered into the first cluster. I change it to 2, it will be all the examples clustered into the second cluster. So what we're going to do is we're going to plot a lot of these on top of each other, and each cluster is going to have a different color. So color here, this is for the 0th cluster, we'll call it blue. Or red, I guess. Why not? Now we're just going to copy this 10 times. 3, 4, 5, 6, 7, 8, 9, 10. And we're going to change each one of these to a different cluster, and each one of these to a different color. And for the sake of time, I'll just copy in what I already have, so I don't have to do it here. And you can see everything is a new color for each cluster, and for each cluster we're going to be plotting its PC1 value against its PC2 value for each example. Alright, now let's take a look at what that looks like. And there we go. So all 10 clusters each of the 10 clusters has a different color, and here I should put the labels on it so we can see. Plot.x label is going to be PC1, and y label is PC2. So here's PC1, here's PC2 for each example, and depending on the example's cluster assignment, it has a different color. So there's only one last thing to do, which is let's put the cluster centroids, which we transformed into 2 dimensions, right on top. So right here we'll say another scatter plot top, which will be our reduced centers. Remember before we had that, where is it? Here. We transformed the cluster centers to be reduced centers in 2 dimensions. So our reduced centers and all rows in the first column, and we'll plot it against reduced centers, all rows in the second column. And this one will make the color black, we'll make the marker an X, and we will make the size, we'll make it big, 300. Alright. Oh, what's wrong here? Invalid syntax. Let me see. Oh, I didn't put the equals for marker. Alright. And there you can see. So each cluster now has a black X marking its centroid. And we can see that the market has now been segmented into 10 different clusters. Again, for the actual data, we would be looking at this, where is it? This guy. No. This thing. How do I say it? Basically, we're not going to be, the PCA is only for visualization. So we can only see this graph if we bring it down to 2 dimensions. Normally it's in 4 dimensions, and that is our actual data right here. And so, but all these guys have been clustered into 10 different clusters, and this is just helping us visualize that. Alright, thanks so much for watching, guys. This is the end of the video. If you liked it, make sure to leave a thumbs up and hit the subscribe button, and leave a comment below with any recommendations or suggestions you might have. I'll see you guys tomorrow, and I hope you're enjoying the videos.